Okay, so the lesson we're going to look at for the first week is a little bit more with graphing calculators, and then section 1.3, we'll do the first part of it, and I don't think we're going to use graphing calculators as much there. We usually use them every day, especially through the first 5 chapters. But there might be a day here or there where we don't do as much with them. All right, so what I'm about to write down is just kind of some general tips for solving, maybe not even math problems, but just really any problem. Just kind of giving you a few tools to kind of work with that you can use throughout the year. So the first thing I have to do when I'm trying to solve something is read the problem they've given you and just kind of make sure you read it and then start to break it down. Understand what are they giving me for information and what am I being asked to find. Because if you read a problem and you don't understand the difference between the information they're giving you and what they're asking you to do, then we can't even figure out how to do it because we don't even know what they want us to do, right? So that could be a little tricky. Sometimes the directions, when you read something, like you're going to come across directions at some point that say, round your answer with an error of at most 0.01. That's just a way of the book saying round to 2 decimal places. Okay. So when on a test, you'd be able to ask me that. When you see it for homework, if you don't really have anyone you can ask, it's like, well, what does that mean? Right? So sometimes it might be a little confusing and we might have to just clarify directions. That's usually the biggest problem people have sometimes with that. So once you read it and you figured out what you know, what they want you to find, you figure out how we're going to approach this problem. Okay, what are we going to do? Are we going to research it more? Like if I was doing a problem, like I had to replace a voltage regulator in my generator. Never done it before, so I had to figure out, okay, I know what the problem is, how do I do it? So am I going to go on YouTube and watch somebody else do it? That's probably the easiest way. Or am I going to call the company and maybe they can send me some instructions on how to do it? But I got to come up with some kind of plan. Right? So in math, picture is always a great tool, especially when we get into trigonometry and we're trying to visualize, like, okay, the height of the building is 200 feet, the shadow is 50 feet, you're standing at the edge of the shadow, what's the angle if you look up at the top of the building? Sometimes a picture just makes that easier. Making a list can be helpful. Like if I said to you, take the letters A, B, C and tell me all the different ways you can arrange them. ABC, CBA, CAB, BAC, whatever. All the different ways. And then you count them. You say, oh, there's 6. Well, for that amount of letters, it wasn't bad. Bless you. But sometimes lists can get big, right? It can get kind of big really quick. And a list isn't always the best way to do things. But for small problems, sometimes a list is good. Most every problem in math is going to involve setting up an equation. Okay? Certainly if I gave you the letters A, B, C and I said just permute them all the ways that you can, there's no equation to do that. Maybe you could come up with like a systematic approach to rearranging the letters, but there's no equation. But with that last problem I said about the height of the building, you'd be using trigonometry. So it'd be a combination of a picture and an equation. And then I think on page 13, they have other strategies you can use when you're trying to solve the problem. Okay, so once you read the problem, you've drawn your picture or you've made your equation, now it's time to actually solve it. Okay? So take your equation, solve it. Take your list now that you made and count. Okay, how many are there? 1, 2, 3, 4, 5, 6. So now you actually carry out your plan. Okay, so we're going to look at a problem that I don't think will require me to really teach you anything. You should have enough background information to figure this out. So, company charges $15 to rent a car. And they charge 20 cents for every mile that you drive. The directions say write an equation. Equations have numbers, but equations also have what? Variables. How many variables do you think this equation is going to need? Yep.
Two, one for the total and then one for the amount of miles.
Right, there's going to be two variables. One variable is going to be the total money you spend. The other one is how many miles you drive. Which one is the independent variable? How many miles you drive?
It's the miles driven, it's the independent.
The independent is going to be the miles driven. The dependent variable is going to be the cost. Because the way you would say it is the cost depends on how many miles you drive, right? How many miles you drive depends on the cost. That's kind of, doesn't sound as natural to me. The cost you pay when you're all done driving the car is going to be dependent on how far you drove. Okay? So for that reason, we'll let X, which is usually the independent, be miles. And Y, which is the dependent, will be cost. Now, if they didn't tell me which letters to use, I might use C for cost and M for miles. But they said to use X and Y. Yeah.
X is usually the dependent?
X is the independent. Y is always your dependent. Yeah. Other than X and Y, if you pick two random letters like Q and R, there's really no standard for that. But X and Y, because of the axes, is the way I just told you. So, anyone think they could give me an equation, and I'm looking for an equation that gives me the cost as a function of how many miles I drive. So one letter by itself on the left equals, and then a formula. Yeah, Vinny?
0.2x plus 15 equals y.
Yeah. Equals y equals same thing. Yep, there's your equation. Y equals 0.2x plus 15. This is a good time, really quick, to bring it up. What's the slope of that?
0.
Yep. And the y-intercept?
15.
Yep. Just making sure we remember that. Okay, so there's our equation. Next thing, they want us to use that equation to make a prediction for the cost. So use your model, use your equation, to find the cost for 50 miles. So how would I do that? How do I take, what do I do with the 50 in my equation to get the cost? Let's see, Alex?
You plug it in for the X and then do you want me to solve it as well or just
Yeah, tell me what to plug in first and then we'll solve it.
So you plug in 50 for X.
Okay, so y equals 0.2.
50 plus 15.
Yep. And if I do that out, that's going to give me
10, and then you add it up, and it's 25 total.
25, and what is that? $25?
$25.
Yep. So it's always important to remember what you're solving for. If it was miles, I would have labeled it miles. That's $25, I'll label it dollars. Okay, now let's do it for 100 miles. Double the mile, double the cost, so should it just be 50?
Yeah.
Quick, done?
No.
Not quite. Why isn't it going to be $50? It's double the miles, so why isn't it double the cost?
Because you're adding 15, so you wouldn't add 15 twice.
Yeah, you're not doubling the 15 part of the cost. You're just doubling the mileage part of the cost. So we're going to get 0.2 times 100 plus 15. And that gives me how much? $35. Yep, $35.
Pesos.
Okay, any questions on that?
No.
Okay. So, that equation right there, y equals 0.2 or 0.20x plus 15, is the algebraic representation of our problem. Like if somebody to walk in right now and look at the board, they would have no idea that this is about renting a car and that you pay 20 cents per mile to rent the car. They would just see an equation with a slope of 0.2 and a y-intercept of 15. We've kind of taken out all the word problem from the information and just made it an equation. Okay. So in the homework, if you see something that says find an algebraic representation of the problem, just make an equation. So, going back to example 1, let's say that Sarah drove the car, and when she was all done, she paid $50 to rent it. I want to know how many miles she drove. What's different? A little bit different here than the last two examples.
You're plugging in for y rather than x.
Yeah, we're going to take the same equation, but we're plugging in for y rather than x. And I'm going to show you two ways to do this one. I'm going to do it algebraically, and then I'm going to show you how to do it on the graphing calculator. Okay. This is a simple enough problem, I can probably do it faster algebraically than using the calculator. Okay, so I've got my equation, y equals 0.2x plus 15. We're going to plug in, as Pat just said, we're going to plug in 50 for y. 50 equals 0.2x plus 15. What's my first step?
Subtract 15.
All right. Last step.
Divide by 0.2.
Divide by 0.2. Divide by 0.2. 0.2 is what as a fraction?
1/5.
It's 1/5. So dividing by a fifth is like multiplying by 5. So really, I'm just trying to think in my head, 35 times 5.
175.
175. Right, so we get 175 miles. That's supposed to be an x. Okay, so algebraic approach in this kind of problem, linear equation, very, very quick. Okay, let's look at how we could do it on the graphing calculator, because I'm going to show you something you probably haven't done unless you've used graphing calculators. All right, so I'm going to look at this right here. I have 50 on one side of the equation, 0.2x plus 15 on the other. So on my calculator, and turn it on, I'm going to go to y equals, and under y1, I'm just going to put in 50. Okay, so the left-hand side of that equation I'm putting is 50. On the right-hand side of the equation, I'm going to put that in y2. So I'm kind of breaking it up into two parts. I'm going to draw a picture of the left-hand side, and then I'm going to draw a picture of the right-hand side. And I want to see where the pictures are equal. Well, that sounds kind of weird. What's a simpler way to say that? Where the pictures are equal to each other.
Where they intersect.
Where they intersect. So I'm going to graph it, and I'm going to look for where the left and the right-hand sides intersect. Okay, so you type it in just like that. I'm going to press zoom 6. Okay, we talked about what that does. It sets a standard window from -10 to 10 on the x and the y-axis. So you know it's working because you got that little yellow circle in the upper right. Still working, still working, still working, all done. Okay, what's wrong?
Your y-intercept is at 15, so you can't even say it.
Yeah, the y-intercept is up at 50. Okay, if you remember, when you graph a line like y equals 50, that's a horizontal line. That's a constant function. Horizontal line at 50. Look at your window. You're only going at 10. It's definitely not high enough. So what I like to do is rather than go put the y max at 50, put the y max at like 60. Then it won't be right on the edge of the screen. Okay, so let's hit graph now. All right, so now we can see y equals 50. But what do I have to do now?
You have to move further to the right, so you can actually see where they intersect.
Yeah, it's getting up there, but it's going to take a while. I already know how far to the right I have to go. I'm only going to 10, right? If I was doing this problem, I might have to guess. Maybe I would try 100, and I would see that that's not enough. Since I know it's 175, I'll do 200. Now I can see my horizontal line at 50. And now I can see that's the line with the slope of 0.2, the y-intercept at 15, and I can see where they cross. To do what we're going to do next, you've got to be able to see where they cross. Any questions up to there? Now we want to calculate where they intersect. Okay, to do that, you press second, trace. Okay, right above trace is the word calc in blue. So second, trace, and you're gonna get that menu. And you can probably figure out which one we're gonna use.
5.
Yep, and use option 5. It's intersect. We'll use 2, 3, 4, and 5 this year. We will never use 6 or 7. That's derivatives and integrals for calculus. Value is kind of pointless. I mean, we could, but we usually don't. So we'll be using 2, 3, 4, and 5. So we press 5. So the first thing it's going to ask you is, okay, tell me the 2 things on the screen that you want to find intersections between. Because maybe you have 4 or 5 lines on the screen. Which 2 do you want to use? We only have 2. So the first curve that I want to use is the one in blue. Or it could be the one in red. It doesn't matter. But you pick one of the 2, and then hit enter. Now it's going to ask me what's the second thing that you want to use to find the intersection. Don't put it on the blue one, because that would mess it up. Okay? You've got to have 1 point on the blue one, 1 point on the red one. Doesn't matter where. You've just said, hey, use the blue and use the red. That's all you're telling it. And now it should look something like that. Now, the third thing it says is guess. The guess isn't really important here. Okay, you could just hit enter and it'll work fine. When the guess becomes important is when you have something like this. If you have something that crosses twice, the calculator only gives you 1 at a time. If you take your guess and you slide it over here, or in this case, you slide it closer to this intersection point, it'll give you that one. If you move your guess closer to the other one, it'll give you that one. If you wanted both, you got to do it twice. Okay? Just moving your guess. Okay? Like I said here, the guess doesn't really matter. So you can just hit enter, and it tells me x is 175 and y is 50. Let's put that there. Oh yeah. I do all kinds of technology stuff. So that's in miles. 175 miles, 175 miles. Any questions on that? Yeah.
So for that value, wasn't it, oh, sorry, never mind. Looked at it wrong.
Okay. Anything else? So intersection is something we'll use a lot. Pretty much all year we'll find intersection points for different things. All right, so when you see directions in the book and they ask you to find a viewing rectangle that shows all the important features of a graph, okay, that's called a complete graph. Right? When I started this problem, it was a horrible window. I couldn't see anything. Right? Negative 10 to 10 was awful. If you asked me for a complete graph for this problem, I would say that's a good window. That's fine. I mean, technically, you don't need to go negative on the x-axis because x was miles. You're never going to have negative miles, and you're never going to have negative cost. So, do you really need to show negative 10? Not really. All right. So when they ask you to find a complete graph, all you have to do is write down the window. What did you use for an x-min, x-max, y-min, y-max? Those 4 things. X-scale and y-scale, not really important. We just talked about how that changes the tick marks. I don't really ever bother with that at all. Yeah.
So it could be a variety of like the answer. Obviously, like at one point it's wrong, but
yeah, like you could say, I mean, if you did 205, that would be fine. If you did 210, that's fine. If you did something like 20,000, I mean, I would say that that's not really a good window.
right.
Because to me, this red line, it looks like it's almost vertical, like straight up. And I can't even really tell what's going on. So that's a little too big. But there's a range of answers that would be acceptable.
You will accept the negative 10, the negative 10 for the...
Yeah, that's fine. Yep. The only time I wouldn't is if I said, show me a window in the context and make sure you take into account like the real world problem. So if it's a problem about a real world thing and it says take into account like whether or not you should include negatives, you should not include negatives if you're talking about like area, volume, population of people, that can't be negative. But unless it specifically says to avoid, be careful with negatives, the window I had before was fine. Alright, so that's actually the problem I did on the first day with you. I graphed a parabola, I shifted it up 10 units, and we saw that it went off the screen. So rather than do it again, I'm just going to ask you, since it was shifted up 10 units from a standard window, which is negative 10 to 10 on everything, which one of the four values would you have to fix? X min, X max, Y min, or Y max? Just the Y max. Yep. And if you put it at like 11, now you're just barely going to see the tip of a parabola. I would say put it up at like 20 or 25. If you can see a U shape, that's pretty good. Now, if you put it up too tall, if you put it up at like 50,000, it's going to make the parabola look very squished and look almost flat. So that'd be too much. Right? Is there any question on how you would do that one? You just have to adjust the Y max from a standard window. Okay. If you type it in on this window, then we might have to fix like X max at 20,000. That's awful. So we'd have some other things to fix. Do zoom 6 and it'll put it back in a standard window. The other thing about the graphing calculator is it distorts what you see a little bit. So if you look at the screen, is it square? No, it's rectangular. So if you do a standard window, which is zoom 6, and if you ever have to stop it, you can press second off and it'll stop it. Because sometimes you can put a graph in that would take like hours if you put in a really complicated one, or you accidentally put in something that creates a problem. You need to stop it. Second off will stop it. All right, so back to what I was saying. So if you do zoom 6, you've basically gone from negative 10 to 10 on the X, negative 10 to 10 on the Y. That's exactly the same distance on each axis. But the screen is wider than it is tall. So watch what happens if I graph a circle using a standard window. Well, you tell me, what's going to happen?
It's going to be elliptical.
Yeah. I'm going to keep my window. There's some other stuff here. Don't worry about that. But it's negative 10 to 10, negative 10 to 10. I'm going to put in a circle. Let's do R equals, I'll make a circle with a radius of 5. And if you look at it, it does have a radius of 5. If you count, it's 5 units in every direction. So the way I can make it look square is if I go zoom square. That'll show you things proportional. Now, when you're graphing a line in an intersection, it wasn't really important that we see it proportional, but a circle is kind of important if you want it to look like a circle. So press zoom 5, and that's as good as you're going to get. So if you look at it, look at your window. About 16.1, and it left that as 10. So that's the ratio. 16.1 divided by 10 is 1.6. That's about the ratio of the width to height, about 1.6. So if you want to set up a window yourself and make it look square, you can put in anything you want for the y's. Then multiply that value by 1.6, and that's your x's. Okay? And that will set things to a square-looking window. Any question on that idea? So that's the aspect ratio of your screen. It's about 1.6. We're not really doing a lot with circles yet, so that's not critical, but just something I thought of. So if we were to graph that like I think we did on the first day, that curve is called a parabola. X squared plus 10 is really one of the simplest parabolas you could have because A is 1, B was 0. So there was no middle term. But a parabola can look like that, ax squared plus bx plus c. Okay, that's called the general form of a quadratic equation, which when you draw it, looks like a parabola. This number, very important, tells you that it's a quadratic. It also tells you, if you subtract 1 from that number, it tells you how many turns the graph can take. So a parabola is allowed to turn 1 time. If your highest exponent was a 3, your graph would be allowed to turn 2 times. So it could look something like this. 1, 2 turns. Okay? Could. Just because you have an exponent of 3 doesn't mean that the graph is going to turn 2 times. It's an upper limit on how many times it could turn, if it feels like it. Okay? So that number kind of gives you a maximum on the number of turns a graph could take.
But a parabola needs only 2. Means the highest power must be 2, right?
Yep. Yep. So if the highest power is 2, it tells you that the graph can turn at most once. Yep. Okay. Let's find a complete graph of this one. So that's a square root function. And we're dealing with the real number system. You don't think about imaginaries. So when you take square roots, is there any restriction on what you are allowed and not allowed to do? Yep.
Well, if we're not doing the imaginary number system, there can't be any negatives.
Can't be any negatives. Okay? Can't take the square root of a negative number. Can you take the square root of 0?
Yes.
Yes. What number times itself is 0?
0.
0. So you can take the square root of 0. So you can take the square root of any non-negative number, or you could say any positive number plus 0, because 0 is not positive. So any non-negative number is fine. So think about x. X can't be anything you want. X couldn't be negative 100. That'd be a problem if you tried to plug that in. What numbers would be okay to plug in for x so that I don't end up with a negative under the square root? Yep.
Negative 20 or above.
Negative 20 and up. Negative 20, negative 19, 18. Okay. So that kind of tells me where my x min, x max should be. Let's go back to function. Y equals. To get a square root, you press second, and then the x squared button. X plus 20. So I know that I can't go past negative 20. But since I don't want my graph right on the edge of the screen, I'm going to go to negative 25. I'm not worried about making this look proportionally correct because it's not circular. If you just pick random values, might it distort it a little bit? Yeah, but you'll get the general idea. Now, x max. What's the highest number you could plug in for x?
Anything.
Anything. You could take the square root of 1,000,000 plus 20, 2,000,000 plus 20, 20,000,000 plus 20. You can really go as high as you want. So let's go up to like, I don't know, 200. Now, this symbol here means principal square root. There's only one answer, and it's positive. If they want the negative answer when you do a square root, you would see this. Positive plus or minus, like you do in the quadratic formula. Without the minus, it's just one answer. Okay, since it's always positive, I'm not worried about going into the negatives. I can leave that at negative 10. I don't really even need to go that low, but that's okay. Now, think about your graph a little bit. If you plug in the biggest value that we have on the screen, 200, you get the square root of 220, which would be about what number? Pretty close to 15. 15 times 15 is 225. So it's actually just under 15. It's like 14.9 maybe. So for my y max, I might set it at 230, and that's plenty. So let's look at our graph. Oh, I didn't mean to set that at 230. I meant to set it at what was just set, 15. If you set it at 230, it doesn't look good. Set it at 15, that's what you want. So that's what a square root function looks like. It has a starting point, and it only goes in one direction. It doesn't go to the left. Like a line goes on forever. This doesn't, because the square root can't go to the left. That's undefined. Yeah.
Why does it start at the starting point it starts at?
It has to do with this number right here. Because if you plug in negative 20, that's the smallest number you can plug in and still get an answer. If you go negative 21, negative 21 plus 20 is negative 1, and now the square root of negative 1 is I. We can't graph imaginaries on here. So it starts there because we're only graphing the real answers to that problem. If you did plus 10, then the smallest value you would be able to do is minus 10.
So why does it go to the minus 10? Because that's the smallest it can do. Is it because it needs the y-intercept or something? I don't know.
Well, think about if you make a table, and you plug in negative 20 for x, what's negative 20 plus 20?
0.
0, and what's the square root of 0?
0.
So y equals 0. That's why it starts where it does. Because if you plug in negative 20 for x, you get 0 for y. Now, could we make this graph not start right on the axis? Sure. If I put a plus 8 on the end, that would actually take that graph and move it up 8 units now. And it would start at the point negative 20, comma 8. But we're going to learn more that later on. Basically what that plus 20 does is it shifts it to the left 20 units. A normal square root function looks like this. Starts from the origin. When you put a plus 20 under the root, it shifts it left 20 units.
And you don't have to put parentheses around the x to get it to move I don't know. Because I was working on transformations a little bit.
Yeah, we'll learn more about transformations, but basically, I'm not going to go through all of it. Where I have the 4 boxes in that problem, that would control the 4 transformations you can do to the square root function. You can shift it left and right. You can shift up and down. You can stretch left and right, and you can stretch up and down. Those are the four basic transformations, and that's for every function we ever studied out here. Shift, 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 stretching or compressing, stretching or compressing. All right. So that's, this number causes a shift. Was there another question?
I figured it out.
Okay. All right. Graphing data points. I'll show you this part. It's not something we do a lot. We will do it a little bit later on, but you can actually plug coordinates into the calculator and almost make like a scatter plot. Okay. So let's say you want to, let's go like this. We want to graph those points on the calculator. Okay. Take my calculator. And first thing I'm going to do is press stat. So stat is in the 3rd column, 2nd row, right by the arrows. Stat. Okay, you got different options across the top, but I'm going to go to edit. Now, if you're missing an L1, L2, L3, or L4, it's because somebody accidentally deleted it. You can get it back by resetting your calculator the way I showed you. But just don't highlight. Now I'm on L1. If I press delete, I'm going to mess up my calculator. Okay, I'm going to have to reset it to get it back. So make sure you are highlighted right where I am. And type all your x's in L1. -3, I might not do them all. I'm just going to do a few of them. -2, -1, 0. Oh, I'll just do them all. Maybe I can't do them that fast. And put all your y's in L2. The way you get over to L2 is you just press the right arrow. Okay, so I typed all those in. Now, if I go to graph right now, you're not going to see anything. You've typed in all these numbers into this list. If I hit graph, it hasn't done anything. Okay. So once you type them in, you don't have to save or anything. They're saved. You can just press second, quit, and you can get out of it, and they're all still there. Okay. What you want to do is press y equals, and if you have anything else in there, we're going to get rid of it. Like I don't want to see that square root anymore. I'm just going to clear it. And I'm going to turn on one of my scatter plots. It really doesn't matter which one you turn on, but if you press up, now plot 1 is highlighted. You just hit enter to turn it on. Now it's on. Okay, it's on because if you press down, you can see it's highlighted. Now, so you just turned on the scatter plot. The only thing we have to do is make sure in our window that we can see all these x values. What's the smallest x value in that table? So that might go -5. Largest x value? So +5. What would be a good value for my y min? Yeah, -20, so it's not right on the edge. And I think y max would also be 20. That's fine. Now, if you've typed them in, and you've turned the scatter plot on, and you've set your window, you can press graph, and you will see the coordinates we just typed in. Yeah.
How was it you reset the size of the graph?
To the standard window?
Yeah.
Zoom 6.
All right.
That'll reset everything -10 to 10. Which you'll see some of these points, but a couple of them, actually the first and the last one, would be off the screen. All right. So we get a nice curve. And if I wanted, I'm going to show you this. You don't have to just watch this. You don't have to do this part. But I can go to Stat, Calc, Cubic Regression, and hit Calculate. Watch what happens. Gives me an equation. And it says, if I plug in all those numbers, it says x cubed minus 3x. Yeah, just watch this part. Okay. If I just plug in these numbers here, it's 1x cubed minus 3x. Okay. Watch this. 1x cubed minus 3x. So what the calculator just did is it found an equation for me that perfectly goes through the points I typed in. So if you had like a lab and you had data, you could type in all your data. You could use the calculator to find an equation of a curve that fits your data. Now, it's not always perfect. I picked this data to be perfect. But you can get a curve that kind of approximates your data. So then you could make a prediction and say, maybe this is time in an experiment. So then you could say, well, at 10 minutes, how many bacteria am I going to have? And I could use the formula that I just made to figure it out. Okay, we're not really getting into that, but I'm just showing you why you would graph points on a calculator for what I just showed you.
Could there ever be an instance where your points can't be graphed?
No, you can always graph your points. It's sometimes you can't find a good equation. Like if you put in points that look like this,
Just kind of choose which ones it wants to use.
it's probably like if you say try to fit a line to the data, it's probably going to go like that. it's gonna draw the best line that it can. If you said fit a curve to the data, you can choose.
So you could use that as a scatter plot tool too to find the line of best fit.
Yep, you can definitely use it for a line of best fit.
So,
What I just did there was a curve of best fit.
Okay.
And I knew that the curve, I knew it was a cubic. I could try to fit a parabola to that data. If it did a parabola, I don't know, it's not a good data set for a parabola. Parabola data set might look something like this. You got points like that, and then it would kind of fit a curve the best that it can. But I think it can do parabolas, cubics,
That's my own, so it's fine.
and quartics. If you have a data set that turns more than 4 times, the calculator can't do it.
We dropped that thing like 5 times last year.
Mr. Hager.
Oh, step 4, we did it, but I didn't have you write it. Set your window, your mins and maxes,
You lose the
and then press
calculator.
graph.
Well, the calculator will warn you, like, let's say you
Yeah.
had points that were really far off the graph, or just say there's something off your display.
Mm-hmm.
The calculator, like, is there a way that you could figure out if you had data that's off the display?
No, I won't warn you. No, if you've got a point that's like 2,300 and it's way off the screen, you just have to know it's there because you typed it in. Yeah, the calculator won't warn you about things that are off the screen. No. The only way to find them is to zoom out and start
Should
looking.
hire you to make the next calculator.
Okay, so last thing we'll look at, we'll go through really quick, not all of the section, but just a little bit on functions. So I already kind of threw a lot of this in as we were doing the first section. But someone had asked, I had asked you guys, which one would you have as the independent? Which one would be the dependent? I'm just writing it down now. So X is always your independent. Okay, that's called your domain. You can also call it the input. Y is always your output. It's your dependent. You can call it the range. Okay, it's just really a bunch of different names for the same thing. So we've talked about equations. Now I'm going to talk specifically about what makes something a function. Well, when I drew a circle on the screen, that was not a function. Okay, there's something called the vertical line test. It fails that. But if you don't want to talk about it in terms of the vertical line test, you can basically say for every input, there is exactly one output. Meaning, you tell me a value to plug in, and I will always give you the same value back out of the formula. It never changes. And where that wouldn't work is something like this. Say you plug in 4 for x. That's the input. What's the positive square root of 4? 2. And what's the negative square root of 4?
2.
Not the square root of -4, the negative square root of 4. -2. So if you did this, your input is 4, your output is 2 and -2. That's not one output, you got 2. Okay? So for something to be a function, you can only get one output. For every x value you plug in, you get one output in the y. And another way to think about it, and I think I mentioned it, is the vertical line test. If you were to graph this right here, well, I showed you guys what the square root function looked like. The negative would flip it. It would basically look like a parabola on its side. Fails the vertical line test. Don't worry about that. So domain, just another way of saying the same thing. I already wrote this down up above. Domain is the input, it's what you can plug in. Range is the output. Now, I wrote valid because when you have a function, not everything is valid to plug in. The domain of this includes all kinds of things, but it doesn't include what number. What number for x would you never allow to plug into that? Yeah?
2.
2. So I would say the domain of this is everything except 2. Because if I plug in 2, it causes me to divide by 0. 2 is not valid. Okay? Unless otherwise stated, we're working in the real number system. So domain has to be a real number. That comes into play when we did the square root problem. Okay? The domain was only numbers bigger than negative 20, or equal to negative 20. I actually just used this notation already. You can write y equals, which is what the calculator uses, or this notation right here. How do you pronounce that?
Function of x.
Yeah, f of x. And it doesn't have to be an f, it could be g of x, h of x. It just, the f is just the name. So this is function f. This is function g. Okay. So it just gives a name to a function. Any question on that? I'm not going to do the complete graph on the calculator because we've done a lot with that. Let's just find, if we need the calculator, we can, but let's see if we can figure it out without it. The domain and the range. What numbers are you allowed to plug in for x there? If you get stuck, think of what you have to avoid with square roots. Yeah, Derek.
3 above.
You can plug in any number 3 or above. So the domain, 2 ways to write it. X is greater than or equal to 3. If you say, well, why not 2? Why can't you plug in 2? Try it. 2 minus 3 is negative 1. You can't take the square root of negative 1. We're dealing with reals. So you can write the domain that way. Or, what's that?
You can also not have zeros.
You can take the square root of 0. If you try it on the calculator, it'll just say 0. Yep, square root of 0 is 0. That's okay. The other way you can write the domain is like this. From 3, with a bracket, it means to include up to infinity, parenthesis. Put a parenthesis on infinity because you can never reach infinity. So I can't include it because I can't ever get to it. So this means 3, including 3, to infinity. Now if I put a parenthesis on the 3, that would be like doing this. Greater than 3. But the bracket means you can include it. Now the range. For this, it might be helpful to look at the calculator, just to kind of get an idea. Let's do the square root of x minus 3. Once we get good with transformations, you'll know the minus 3 is shifting at 3 units to the right. Let's just go zoom 6. Now I still have my scatter plot on, so I should probably shut that off at some point because that's kind of distracting. But look at how high and low the graph in blue goes. What does it look like the lowest it ever goes is? 0. And how about the highest? Infinite. It's going to keep going up. It goes up slow, but it will keep rising as you go to the right. So the range is everything greater than or equal to 0, or 0 to infinity. I'm showing you interval. This is called interval notation on the right. This is like inequality notation on the left. We're going to start using interval notation more later on. So.
If we write it like one way, do you want us to write it the other way for range?
No, you can write it whichever way. I would just stick with the same way.
Right, okay.
Yeah. Okay, x squared minus 4. When you have a graph and the highest exponent is a 2, what does it look like? Parabola. Is there any number that you are not allowed to square? No. You can square zeros, positives, negatives, fractions, decimals. So what do you think the domain is?
All real numbers.
You can write all reals, or what you'll see me write a lot is this. Negative infinity to infinity, always a parenthesis because you can't reach it. Okay, you can't
If you
put
put infinity to infinity, would that be considered correct? Or it doesn't have to be negative?
negative infinity to positive infinity.
Okay.
Yep, means you can go as negative as you want and as positive as you want. And now let's graph it. Does a parabola go up and down forever? No. It does go one way forever. But if you look at that, what does it look like the lowest value the parabola hits is? -4. And the highest? Infinity. And you can actually, if you weren't sure that it hit -4, you can calculate the minimum value that it hits. I'm not going to go through it because I think it's pretty clear. You can see it's -4. All right. This one I'll do just to show you where the absolute value button is. So if you want to type in absolute value, it's math, number, and it's the first option. ABS stands for absolute value. X squared minus 4. All that absolute value is going to do is make everything positive. So whatever parts of the graph were already above the y-axis are going to stay the same. The parts that dipped below are going to be flipped up to become positive.
It's gonna have like 3 curves.
Yep, so it's going to look like that.
It's a W. Okay. Like what I take.
The part that was down here has been flipped up. So what's the domain of that now? It's the same. You can still square any number you want. That's what you plug in. Right? So that's the same. But the range has been affected. The range is no longer -4 to infinity.
0 to infinity.
It's 0 to infinity. Yep. So I did that more just to show you where the absolute value button is. It's math, number, and then it's the first option, option 1. Math, number, option 1. Evaluating. All right. So you don't really have to write that down. It just tells you to evaluate. You plug in the number. So let's try a couple of these. Take the number they tell you to plug in parentheses, change the variable to that number or letter, and that's it. So in this case, -2 is what I'm plugging in. -2 squared plus 1. So what is the value of the function when you plug in -2? 5. Yeah. How about, we'll probably do this one without even writing it. What's the value of the function when you plug in 3? 10. What's the value of the function when you plug in a? You can't do much with it, a squared plus 1. The value of the function when you plug in x minus 3. Well, let's write it first and then be careful.
X squared minus 8.
X squared
Minus 3.
Minus 8.
And then times it again.
Because you squared both.
Remember, this involves foiling,
Uh-oh.
right?
That's what I feared.
X squared.
So-
Then that's minus 3x.
X squared, yep.
Minus 6x
Minus 6x, that's the part I was looking for.
plus 9.
And then a lot of people got the plus 10, which is -3 times -3 plus 1. So that one, you have to remember to FOIL, okay? Any questions on that? All right. We already did all that. I think this is the second to last slide, yeah. So, and actually I already went through this exact thing. Not every equation is a function. If I take this equation, in order to get y by itself, which is the only way you can plug something in on a graphing calculator as a function, gotta get y by itself. You take the square root of each side. I don't think I graphed it. I showed it to you, but let me graph it. Square root of x and the negative square root of x. What's good is it's in two different colors, so you're going to be able to see exactly which one is which. There's the square root of x. There's the negative square root of x. It's a parabola on its side. So if you were to draw a vertical line, it fails the vertical line test. Okay, so vertical line test says if you can put a vertical line anywhere and it hits the graph more than once, it is not a
I
function.
think that's the only normal name there is in math. I'm surprised some philosopher didn't like
Change
make
the
it
name.
his test. Like I'm surprised it's not like
Like
someone's
Euler's test
name.
or something?
Yeah.
No, vertical line test. There is a horizontal line test, but we'll talk about that much later. Okay? So, a lot of stuff in that section. Again, hopefully most of the like input, output, domain, range, most of those words I think you've probably heard before. But next week we'll finish up chapter 1 and we'll start to get into chapter 2. Okay, so the homework that I give you, it's due next academic Monday. So this is a little weird. We normally don't have homework today, but it's because we didn't have a test. Okay, and that will be in the video. I'm going to put that online in about 5 minutes. Okay, so page 20, 1 through 10, 18, 21, 29, 32, 38, and then page 30, 1 through 8, 11, 13, 16 to 19, and 24. If you need any help with graphing calculator stuff, feel free to send me an email. Like if you watched my video but you couldn't figure it out. I do need to tell you the password. Don't say it if I already told you, but did I tell you guys the password yet? No. Alright, there's a file in the video that needs a password, and I'll tell you that in a minute, if you want to download it offline.
That's for the calculator.
Yes.